Hello, everyone. I am Giannella from University of Salerno, Italy. So I'm presenting you today a work within the framework of the probabilistic fracture mechanics. The problem is rather complex and hard to be explained in a very brief oral presentation. However, I'll try to do my best in explaining what we have done here. So the physical process we are dealing with is the fatigue regrowth in metal materials that we know as a statistical nature. This is due to the fact that there are numerous potential contributors that can affect this process. As instance, if considering the simple CT specimen shown here in this slide, we generally obtain, after a fatigue test, what is generally called as a crack propagation life, that is this chart at right. So, however, this curve is actually different for any experimental test we perform, and this is due to assistance, the material itself, the loading condition, the processes, the geometrical tolerances, measurement, human judgment errors, and so on, the environmental condition, and so on. So, we will focus only on these three sources of variability here in the red boxes in this presentation. And with that in mind, so we aimed at investigating this phenomenon of fatigue regrowth with reference to the first stage compressor of a turbofan engine that is shown here. And we considered three primary contributors of uncertainty that are affecting the life prediction accuracy of this component. That is the material scattering, namely the material exhibits a certain variability in its resistance against K growth. And this has to be considered in some way. Then the second are the geometrical tolerances. And in particular, we consider the variability of the fillet radius between at the blade's roots. And this is one of the most critical positions for this component. And therefore, we would expect a sort of notch effect given by this dimension. The third one, the third uncertainty source is simply the rotational speed of the engine that obviously is continuously varying during the service life of the engine. So starting from those that are generally called uncertainty or variability sources, in this work, we try to quantify their impact on the life prediction, on the residual life prediction accuracy of this component. So the purpose is not only to get a quantification of their impact, not only to achieve a probabilistic and robust structural integrity assessment, but also to allow for a better comprehension of the fatigue regrowth processes, understand what is important, what is not, so as to eventually suggest improvements to standards, algorithms, creating black boxes, models, and so on. So, to this aim, the procedure we came up with is based on a synergy between Monte Carlo simulations and numerical simulation via finite linear method. So here in this slide, we are looking at a macro example of how one Monte Carlo simulation works. So each simulation considers a fillet radius dimension according to the probability distribution function we can see at the top of the slide. So basically, we assume that this dimension has a mean value of 1.5 millimeter and has an allowable range of variability of plus minus 1 according to this distribution. Then we assume a rotational speed according to this second probability distribution function. So again, we are assuming that the rotational speed of the engine is 30,000 RPM and could have a plus minus 15 to 20% of variation according to literature data. Then we extract two data for each simulation. Then we derive a NASGRO curve that fits the experimental data, one new NASGRO curve for each simulation. According to these three, starting from these three data, we derive a life distribution deterministically. So this is one Monte Carlo simulation. Looking at the further simulation, then we change the fillet radius according to this distribution. We change the NASGRO curve according to this experimental data. And then we change the rotational speed according to this distribution again. And then we perform again another life prediction. So after many simulations, we can obtain some results such as probabilistic life assessments or sensitivity analysis, quantification, uncertainty quantification, and so on. This is a macroscopic viewpoint of how the Monte Carlo simulation procedure works. And now we will see a brief description of the preliminary numerical simulations that we needed to set up this procedure. So basically, we used the numerical simulations to derive the K values as a function of fillet radius, rotational speed, and crack size. So we built up various finite element models by considering different fillet radius sizes. So these are some of these CAD models that we considered. The rotational speed was the only loading condition that we considered. So fixed at the nominal value of 30,000 RPM and variable, and we will see how we modified this. This is an example of the maximum principal stress field that we obtained in this model, and we can see also the variation of the peak values of the maximum principal stress as a function of the fillet radius values. So this graph suggests that these parameters has a great importance for the crack nucleation life, and we try to understand in this work if this happened also, if the same also happened with reference to the crack propagation life. So we performed various crack growth simulation, assuming a crack in the most critical position, that is here. These simulations are generally conducted as step by step, then incrementally starting from the nucleated crack and up to failure. This is an example of the local maximum principal stress in the crack insertion area. So as I anticipated, the simulation were performed step by step incrementally, and we repeated some simulations for various fillet radius. This at left is an example of the growth direction that we observed. So the crack propagated perpendicular to the maximum principal stress, then parallel to the tangential stress, then the crack propagated radially. This is the evolution of the crack shape, where we wanted to highlight the growth direction, the final front of the crack, and then the path along which we extracted the K values. K values that are reported here in this chart as a function of the crack size. So we repeated this calculation for various fillet radius dimensions, and we derived this series of curves where we highlighted some patterns depending on the fillet radius size. And finally, according to the simple linear relationship here at the bottom right corner of this slide, we were able to calculate the K values as a function of the rotational speed n. So the last passage we need to explain is how to derive the series of Nesger curves that fit the experimental data. So we started by sampling randomly the parameters, the main Nesger parameters. We draw a curve. So basically we calculated the A over the N. Then we tried to understand, we calculated actually the fitting quality of each curve against the test data. So for example, this is a bad correlating curve. We repeated this calculation many times, so we derived also good correlating curve. We repeated this a lot of times, and then we removed the Nesger curves that did not provide any satisfactory correlation. Then at the end of the calculation, we replicated, we simulated the scatter, the span of the experimental data through many, let's say, equally acceptable values. And we used one curve for each simulation, for each Monte Carlo simulation. So this is the two slides left. So here we can see an example of the probabilistic life assessment we derived, and looking at the total cycles, we can see at the lifespan distribution as a log normal distribution. We derived that the component has a mean value of the life of 10 to the power of 4.4 cycles, so more or less 25,000 cycles. And this actually can vary a lot from as low as 10 to up to even more than 60,000 cycles. This is a noteworthy scatter that is in any case consistent with the similar calculation related to both fatigue and fracture. Then we performed a sensitivity analysis. So we removed the fillet radius uncertainty. So we fixed the R value to 1.5. And then we derived that it actually induces a negligible impact on the life prediction accuracy. So we did the same with the loading condition variability. So we fixed the rotational speed at 30,000 RPM, and we realized that actually this plays a relevant role on the life prediction accuracy. So to obtain a final ranking, material scattering turned out to be the most important contributors. Loading condition definition represent the second most important contribution, whereas the geometrical tolerances played a mostly null role. So to conclude, with this procedure, we wanted to do what we wanted to do in this investigation was to present this procedure. We are not looking at the further results for sake of brevity, but anyway, we can calculate a lot of things. For example, we can calculate the probability of failure within a given number of cycles. We can calculate the probabilistic safety margins we can use directly at the designing stage. We can quantify these uncertainty sources and so on. I concluded, so thank you for your attention, and please, if you have any question, feel free to ask, and I'll try to give you some more quick details.